In this video we're going to take a look at the shooting star challenge on HackTheBox. This is an easy Pwn challenge, and the description says, tired of exploring a never-ending world, you lie down and enjoy the crystal clear sky day. Over 1,000,000 stars are above your head. Enjoy the silence and glorious stars while you rest. So we'll start by trying to get this working locally before we bother booting up the server. Let's take a copy of this shooting star file, copy it over to the local directory, and as usual we'll begin by doing some basic file checks. So we begin by checking the file type, and we'll see that as in our previous exercises we've got a 64-bit LSB executable. This time it's not stripped, so we will be able to resolve symbols and things like that for debugging. If we run checksec -- files, we can get autocomplete, and we'll see that this time as well we have no execute enabled. So if this was disabled, we might want to inject some code onto the stack to execute it, but in this case we're not going to be able to inject any code that we execute onto the stack. We don't have pi enabled, so we don't have to worry about the finding the pi base address. We don't have any stack canaries, don't need to worry about that, and partial railrow is enabled as it has been in the previous examples, so we'll not concern ourselves with that too much at the moment. Let's run strings-m10, and we'll see here some of the libc functions that are imported. We can get an idea what's going on with the program. So we've got some outputs here by the looks of it. We have an options menu. Do we want to make a wish, stare at the stars, or learn about the stars? We can see the C file this was actually compiled from, but we don't really have too much else to go on. There's not really anything else of use there. So let's make this executable and let's try to run it and see what's going on. So if we do /shooting star, we've got this make a wish, hit 1, and just type hello. May your wish come true. Okay, we'll try that again. Do 2, and it just comes back, isn't the sky amazing? Let's do it again. Do 3, and then it prints out this big string that we saw as well. So that appears to be our only avenues, our only functionality. Let's try and make a wish that's longer. Let's do, I'm going to paste some of this in here. Alright, we've got a segmentation fault there, so it looks like we found out where our buffer overflow is anyway. That's cool. So let's move on to, as we have done in the previous examples, let's move on to analysing this in Ghidra. We'll open it up and create a new project. And I would advise, by the way, if you haven't already, go through the Pwn challenges on HackTheBox, the videos which I've been doing in order, because these do step up quite a bit, and again this challenge will step up quite a bit from the last one, so I would recommend checking that out. Let's call this shooting star, and we can do Control and I to import, and just go and find your file. Where's mine? It's desktop ctf HackTheBox Pwn shooting star. Oh, no file system provider. Okay. Was it because I did Control and I there instead of? Okay, let me do file import. Yeah. All right. Control and I doesn't work. It's just because whenever you, okay, forget it. Let's go OK. Double click on this file. Yeah, whenever you got a file there, it has like a capital I beside import file, as if that's the shortcut, but apparently it doesn't work for some reason. So we'll do our default analysis checks here, just let this load up, and because this is not stripped, we can see the functions here. It's not all just been renamed and obfuscated. So instead of having to search for the entry point, which or search for strings and try to identify where the functionality is, we can just click on the main and that'll take us straight to the main method. So what's happening in the main function? We have a setup here where it's just setting some buffer values, setting virtual buffers. Let's go back. We have a write here, so it's writing, let's see what it's writing. It's writing this to the screen. It's writing our menu, a shooting star, make a wish. So we can go back and we can remind ourselves as we're running through this. This is what's happened. It's run setup, and now it's run the write there, and then it will have jumped into star. So the write, as you can see, it's writing. Let me try and make this a bit clearer. It's writing 5b, so 91 characters from this part of the .data section in memory, and then it calls a star function. We open up star function, and this is our menu. If we enter the key 1, it's going to write out 3 bytes from this part of the .data section, which is actually just the 2 angular brackets. So let's do 1. You see now it's showing the 2 angular brackets, so that's all that's happened right there. Is it's done the write, and it's reading from us. It's reading 200. So what's that in decimal? Oh, you can go and highlight this, and you'll see that that's 512 decimal. And then it prints out. It writes to the console, "May your wish come true." So we can type something in there. Hello. And this was where we identified that the vulnerability is. So here's our buffer. It's defined. It's local 48 and it's 64. And yet here we're trying to read in 512 into this local buffer. So there's our vulnerability. If we try to give the option 2 or 3, it's essentially just going to write out some text to the screen. So this doesn't appear to be of any interest to us. So let's go and run this in GDB in PwnDbg, and we'll try and calculate our offset to the instruction pointer, and then we'll talk about what our route to exploitation is going to be. So we can look into doing a return to libc attack on this, because we don't have any. I think in our last challenge we had a system call. It was like calling system date, so we were just able to find the address of that system call and then pass in the string bin sh, which I think was somewhere in memory as well. I can't remember exactly, but in this case we don't have a system call anywhere to go by, so we have these reads and writes, but not too much else. But because read and write are also come from the libc library, they come from the same place that the system function is available and the bin sh string, we can potentially get the addresses of these functions in the libc library and then calculate the offset from there to the functions that we're interested in, like the system function and like the bin sh string. So we'll keep this open in case we want to flick back between our decompiled code and GDB, but for now let's open this up in GDB and see what's going on. So I'm going to open GDB PwnDbg. Let's load the file. I was meant to pass in the file there, but we can just do file load. We can go info functions, and because we don't have it stripped this time, we can see that we've got a star function, we can see we've got a main function, we can grab the addresses of those, and we can see that we have the write and read and things like that, which are in the procedure linkage table. The address of them in the PLT here. So essentially we need to the way we're going to approach this is by trying to use the write at PLT to print out the location of write in the got table, and from there, from the global offset table, we're basically able to access the libc library. So let's not worry about that too much yet. Let's do our cyclic offset. So just to demonstrate, as usual, if you want to find out things you can do in PwnDbg, you can type PwnDbg, get a list of functions here. For example, like ropper, we can go and grab rop gadgets. We can go into radr by hitting R2, do AA to analyze the functions. AFL, we'll get a list of them here. And then we can do s main or s sim.star, and then PDF to disassemble that. We can go and have a look at the code, and etc. We can also, actually, sorry, one other thing I could have done there, we can do is and get the list of sections as well, and then we can find out what size these sections are, whether they're writable and executable. So in some cases we might see that we have this data section with 10 bytes, and we might want to write like the string bin sh there, and then call system with the address of this .data section. If you go back to the ROP Emporium series we did some stuff like that in there. Okay, just a bit of a detour, but let's go back to getting our cyclic pattern. Let's do cyclic I'm going to do cyclic 1000 because it was 500. It took 512 bytes in, even though it into the 64 bytes variable. So let's run this. Let's go to make a wish. Let's paste in that cyclic pattern. Crashes it as it should, and you'll see it didn't put our address. It didn't put our cyclic pattern in the RIP because it's an invalid address, but it would have put these 4 bytes in. So we can do cyclic -l to look up, and there we get 72 bytes. So we need to write 72 bytes before we overwrite the return address. And where do we want to return to? That's going to be the question. So that's what we'll go and look at in PwnTools here. Note that you can also see the rest of this filling up on the stack. So you can see here, if we do stack, let's do x over, we sent 1000 bytes there, let's do x over 1000x RSP. You see there we've got that in hex. Let's go and do it actually in as a string. Oh, let's do it. Let's do 500. Oh, let's do as characters. There we go. Okay, so we get the characters, and then we can see. So we could get an idea how much we actually wrote in there of our pattern as well, and we could find our offset. So let's see right at the end here, our offset. We have AA. So CAAF. So let's do cyclic -l CAAF, and we can see that's 508 bytes in. We've got this part of the string. We could have done that in like PWDer as well, which should give us a slightly, in my opinion, a better layout. So if we do GDB PWDer and pass in shooting star, do pattern underscore create 1000, grab a copy of it. You can actually save this to a variable as well, and then run the program. We'll make a wish, we'll paste that in, and then we'll do pattern underscore search. And this time it tells us as well that our offset was at 72, but it also tells us there that we can write around 203 bytes of our shellcode or something there. Although in this case we're not going to be able to execute shellcode on the stack anyway. Okay, so we've identified the offset, it's 72. We don't need to really worry about it anyway because we're going to be looking for the offset in PwnTools as well. Let's what we could do as well is let's disassemble our main. We have the star here. Let's set a breakpoint at star and let's run the program. You can see it's hit our breakpoint here. Now if we go and say p system, we can find the address of the libc system, and if we go and say p write, we can get the address of our libc write. And it's possible to say in here, if we want to, we can print system -write and get the offset. So we can use these and basically go and plug these straight into our PwnTools script, so that if we want to find, so for example if we find the offset of the write function, we know that we can go and subtract the write function away to get the base address of our libc library, and then we can add the offset of our system function to get that as well. There are plenty of different ways that we can find these, by the way, so I'll demonstrate some other ways as well. We can also search in here as well. If we do search and do search -h, we can search for hex, we can search for bytes, search for strings. So if we do search -s and put in here bin/sh, we'll find actually the location of our bin/sh string as well in libc. So these are all really handy ways of doing this. Let's see how we can do that in some other tools as well, just before we jump into our PwnTools script. So we could do ldd and then shooting star, and we'll get the base address actually of our libc library and also the library itself. So we can say now if we want to find the location of the write function, we can say we'll say read elf -s. We'll paste that in. See here, it'll give us all the function offsets, and then we can say grep system. There we get the offset of our system address. So if we find the base address, all we have to do is add this address to it and we'll get our system. Similarly, we can do write as well. So if we find these are the offsets, but if we find the actual address of the write function in libc, then we can subtract this offset, get back to our base, and then we can add the offset of our system to get our system from that. Hopefully that makes sense. And similarly, if we wanted to, let's grab strings, we'll do strings, paste that in, say grep bin/sh. Oh, we need to, let's do strings-a, strings-a-t. Strings-a-t will give us radix. We want to print it as base 16-tx, and here we go, there's the offset of the bin/sh string. So these are a couple of ways you can do it. There are many more ways, and we'll be able to do a lot of this just through automating in PwnTools as well, but I just thought I'd demonstrate that. And let's go ahead and open up our, we'll take a copy of the template we have, the PwnTools template. We'll call this shooting, or I'll call it star just to make autocomplete a bit easier. I'll call it star.py, and we'll open this up, Codium, star.py, and begin to build up our PwnTools script. So this is the same script that we've used in the previous examples, so you should be familiar with it now. First thing we need to do is set our binary name, so we'll set this to, oh, why is it not letting me, okay, shooting star, and we know it's going to be 64-bit again, so let's go and uncomment the 64-bit version of our IP offset here, and that's the first thing we're going to want to do. Let's go and comment out our code. We're not even going to bother with this, we're just going to be trying to get our interactive shell. Let me take out a couple of things. We're not going to be writing the payload. The only time we really want to write the payload is if it's something we can just send the payload straight to the binary or straight to the server. Anytime where you have to put in some options and things like that, we're not really going to be, there's no point in printing it to a file. And at the end we're going to be wanting to try to get our shells, so let's just throw that in now, get it out of the way. And we're going to comment this stuff out. We're not even going to bother starting the program yet because we're going to try and find the offset first. So we can pass in 1000 there, it doesn't matter. And whenever we pass it in, let's see what happens again. We run shooting star. It asks us, gives us all this text, but really this is the last thing that it gives us, this prompt, so that's fine. Let's go and take a copy of this. There's something wrong with my highlighting, it's like stopping the highlight for some reason. And the option we want to give it is 1, right? We give it 1, it says make a wish, and then it gives us 2 of these, so we can just say, alright, well after you give us 2, we're going to give you the payload, and then it's going to come back with may your wish come true. We're not interested in what it comes back with, we're just going to wait for the program to crash. We're going to analyze the core file to see where our stack pointer is, to see what values in our stack pointer should I say, and that's going to be our offset. So let's run that, and we'll set this to debug so we can see what's going on. And we'll run python star, and you'll see here it came back, it located the RIP offset at 72. So you can see that this is what it sent these 1000 bytes, the cyclic pattern, and the part of the cyclic pattern that ended up there was 72 bytes into this. So we're going to need to put 72 bytes of NOP instructions or A's or whatever. Then we're going to want to put a return address of something that we want to go to, but it's going to be a little more complicated than that this time. So let's get started. Okay, so let me briefly explain the attack again that we're aiming for here. Because we can't execute code on the stack, we're not going to be injecting shellcode like we did in the Jeeves challenge or back computer challenge maybe. We're not going to be able to do that, and because there's no system function in the program, we're not going to be able to just use the address of the system function. We're going to need to return to the libc library that's loaded. But in order to find our way into that libc library, we need to leak an address from the global offset table. So let's, just before we start building this up, let's just have a quick look at what the got and plt are. Okay, so I'll try and give a brief summary here. I'll leave a link to this and article in the description anyway. High level introduction, what's this all about? There are two types of binaries in any system, statically linked and dynamically linked. Statically linked binaries are self-contained, containing all of the code necessary for them to run within a single file and do not depend on any external libraries. Dynamically linked binaries, which are the default when you run GCC as most other compilers, do not include a lot of functions but rely on system libraries to provide a portion of the functionality. So essentially, as it says here, if we use something like printf in a program, it's not actually going to include that the code for printf. Instead, whenever you run the program on your system, it's going to look up printf in some system libraries, so libc, the libc library, and if we go actually and run file again, let's run file shooting star, and you'll actually see here this is dynamically linked rather than statically linked, which some of our previous examples may have been. And what does this mean for us? Well, there are several sections here. We have a global offset table. This is the table of offsets as filled by the linker for external symbols. So for example, our write function, our system function if they're used. And then we have a PLT, procedure linkage table, and these are the stubs that look up the addresses in the got.plt section and either jump to the right addresses or trigger code in the linker to look up the address. So basically, once the code is executed, it's going to populate the address from the global offset table into this got.plt section. So in future, whenever it goes to look up the address in the got, it'll just grab it from here. If it's not already grabbed it from here, it'll need to then find it and populate it. TLDR, those starting with .plt contain stubs to the jump to the target. Those starting with .got are the tables of target addresses. So you can go through and look at an example here, but essentially all we really need to be aware of right now is that if we go to our code, we have these writes, and if we can call the PLT write and get it to write out to us the memory location of the write function in the got, so from the libc, then from there that's basically our entry point to the external library, and we can just start using offsets and things from there. We still need to worry about the version of libc locally compared to what might be running on a server, but there's different things we can do to take care of that later. Alright, so with that out of the way, how are we going to leak this got address? So we'll uncomment some of this code, and because we have our context binary set up here, we've defined the elf. All our bits and architecture and everything's done. We don't need to worry about any of that throughout this, but we can analyze it as well. So in previous examples, you've seen us do elf.symbols, and then we do like elf.symbols.system or .main or whatever to access the functions. Let's print out elf.symbols, and you can see that we have them all here. We have a nice dictionary of keys and values, and we can see our got.write here. So let's actually do elf.symbols.write. We'll print it as hex so we can see the memory address. And let's go ahead and print out, just out of interest, plt.write and got.write. So you see these two are exactly the same here, the PLT and the write, and the got isn't too far off it. This isn't the actual address, which is why we need to leak the address. And let's start doing that now. So if we go back to Ghidra, let's look at the write function. Oops. didn't mean to go into it. Okay, so we can see that a write's occurring here. Basically, for the write function, in fact, let me try and so write, we can see here, write takes in the file descriptor as an integer, it takes in a pointer to the buffer, and then it takes in the size that you want the buffer to be. So calling conventions dictate that. Let's go back to our code. So if we highlight the write function here, we can see that it takes in the int there, the EDI, the buff is the RSI, and then the RDX. And yeah, we can see we have our move RDI here, which is 1, and then we have our RSI is the pointer to this buffer, isn't the sky amazing? Load effective address, you can see there, and then the 18 was our EDX as well. So we basically just need to bear this in mind if we're wanting to call the write function. So if we have we want to get whatever value we want to write into the RSI. So the value we want to write is going to be the memory location, the address of the got.write address, the write address in the global offset table, and we hopefully won't need to worry about the other parameters, the size and things like that. Let's the RSI is going to be the important bit for us. So let's see if we can find a ROP gadget in order to do that. So there's a couple of ways we can do that. We can actually do it inside PwnTools, and I think we'll look at doing that towards the end. But for now, let's do ropper-f, pass in shooting star, and we'll search for pop instructions. Let's grab a pop RDI instruction as well, because we're going to need this later whenever we call our system function. So let's set up a couple of variables. Let's do pop RDI is equal to, and then we'll just put 0x here. We've got a pop RDI instruction. Now let's do pop RSI. If we go back to our ropper, so we don't actually have just a pop RSI on its own, but we've got pop RSI R15, which is fine. We just need to remember to put on an empty value, or you know, some irrelevant value to pop into R15 so as not to mess up our ROP chain. So let's copy this RSI, and because it is RSI R15, we'll want to just name it that just so we remember. And we can do 0x. Let's add in some print statements here. Let's say info, and then we'll format this as hex and say pop RDI, and pass in the pop RDI. And we'll just paste this and do that for pop RSI R15 as well. And let's go start building up a payload. So at the offset, which is 72, we're going to be putting in, first we want our pop RSI R15 instruction, and this is going to pop the next two values. So the next two values we place in here, the first one's going to be popped into the RSI, the second one's going to be popped to the R15. So the RSI, what we want to pop is the elf.got.write address, and then to the R15 we don't care, just pop nothing. And then we want to call the elf.plt.write function, and let's just look at what's happening here. We're popping the elf.got.write into the RSI, that's the address of this, and then we're calling the elf.plt.write function, and because this is in the RSI, the got.write address, it's going to call that as a parameter. So it's going to write the address of the got.write address. That sounds bad. It's going to write the address of got.write to using the plt.write. So if we go back to our code, we know that what happens here is it prints out right here. We have the write, and it prints out a couple of characters. So let's so instead of printing out those characters from the data section, these two angular brackets, we're going to be printing out the address of the got.write function. And then finally, we want to just go back to, or we can go back to our main functions. We'll do elf.symbols. This is just the return address .main, because this is going to run through, and after it's done that, we want to go back and do our exploit, right? So we're doing this to leak our got address, but then we want to go and use that got address to get the system address and then call system. So we want to do now the same. We want to overflow the buffer with this payload that we've got. So we're doing the same thing we did up here to find the IP. Let's paste this in here, and we're sending 1, and then we're sending the payload. Let's just update this to IO, and we'll send that off, and then let's have a look and see what we get back. If we have this on debug, it should just come back with what we need. Let's run it. And did it show our leaked address? It actually didn't. Okay, let's do print io.receive. Run that. And okay. Let's go back. Let's try and receive lines. Can't remember exactly what the output is. Oh, the output that's coming back to us is... Alright, let's run this. Let's run shooting star 1, we make a wish, we get this may your wish come true. So let's go back and let's say io.receive until we get this, may your wish come true. You can take the new line as well, we don't want that. And then hopefully, let's do then print io.receive, what comes after that. There shouldn't be anything which comes after it. Let's go back here. So what's happening whenever we do shooting star, we do make a wish, we say, hi, this is my wish, and then it says, may your wish come true, and that's it. But if we now run this with our code, it's going to overflow the buffer with our 72 bytes, and then it's going to pop our got.write address into the RSI, and this useless value that we don't need into the R15 because we couldn't find a better gadget. And then it's going to call our write function, which is going to then print this out, and then it's going to go back to the main. So hopefully, if we run this, that should all happen for us. And look at that, that's looking good. So this is printed out in hex. We need to extract this. So what we'll do is say, let's say our leaked address is equal to, we're receiving that, and then we need to extract and format it. So we can say got.write, so our got.write address, our leaked got.write address is unpack, and we're going to unpack our leaked address. We're going to grab the first 6 bytes of it, and we can do .ljust in case we need to justify it with zeros. So we'll do ljust and say 8, and then we can do just with null bytes. And then let's copy one of these print statements. Let's do info, and we'll say that the leaked got.write is equal to this got.write, and hopefully we got it right. Leaked got.write. Alright, so that's looking good. Let's actually, what we can do, let's set a breakpoint at star. B star, we'll break at the star function, and let's run that and just type in GDB capital letters. That'll bring up our GDB debugger, and see there it's set our breakpoint, and let's hit continue. I think it's just going to end now because we didn't have any other breaks. Okay, but let's see if we can have a look. Our leaked got address there. If we say, in fact, can we just go got? Let's do got. Oh, program's not being run. Okay, let's run that. Let's do that again. And I'm gonna see. Can we check now? Okay. Let's close that. Let me change our breakpoint to main. I think that's a good idea because we're going to jump back to main. So that should be an easy way of doing this. Oh, let me. Okay, so we get a pop RDI. All right, cool. Let's continue. Okay. Yeah, program's not being run. Okay, we can. Let me go back again. We're gonna say. I'm gonna uncomment this. And hopefully that'll just keep it running. I could have just done the IO interactive there actually. I think. Okay, try it again. Hit continue. Switch to the interactive mode. Our program's still running by the looks of it. So now if we do got, and we get our gots here. What was the leaked address? This one ended in 20. And if we look here and see our write address, we'll see it's 20. So remember we've printed out at the beginning our got.write, and it printed out as this. So this was the address basically in the PLT, I guess, that it's not actually been resolved to the external library yet, if that makes sense. So this is great. We know that we've correctly leaked our got.write address. We verified it here, and this means that we can go ahead and start calculating offsets. So we can go and subtract now the write offset, the offset of the write function, to identify where's the base of libc, and then we can go and add the offset of the system function to call system and things like that. So let's go and start putting that together. Right, so let's look first of all at let's do the LDD again. LDD and shooting star. Let's get our libc address, and we'll do readelf-s. Oh, it's not letting me. Oh, weird. Readelf-s, and then we'll grep the write function, write, and we'll see here that this was the offset of write from the libc. So now we can go and say, well, if we wanted to get our libc base address, we'd say libc base is equal to the got.write that we just got minus the offset from the base that we've just identified using readelf. That's one way we can do it. Another way we could do it, we could say subtract the elf.plt.write, or we could do, yeah, I think we could do elf.plt.write there. But let's do this manually with the addresses that we can find using readelf and things like that. So we'll go back here. What else do we need? We've now got the base address. So if we wanted to get the system address, we could say system address is equal to our libc base plus, and what's the offset of system? Let's grep system from libc. This is the offset from the base, so let's copy that. And let's paste. Oh, why did that paste in there? Okay, let's paste that in there. There's our offset. We don't need to worry about how many zeros and stuff we have in here. We have a context set, so it knows what operating system and what architecture and things like that we use, and we don't need to worry about any of that. So there we go. We've calculated our libc base. We've calculated our system address. So we also need our bin sh as well. So let's go and let's do this again. We want to grep the /bin/sh this time, but rather than read elf, we want to do strings dash what did we need to do last time? Strings dash t dash a. Strings dash t dash x, my bad. Okay, so we get that offset, and we can then say bin sh string is equal to the libc base plus the offset. So we could go ahead and print some of these out as well, just to verify things. I'll just paste a few of these here. There's our libc base. There's our system. And there's our bin sh. Alright, let's run through that and just make sure it's all working. And we've printed out the offsets here. We could go, actually I should have done that in GDB, shouldn't I? And yeah, let's do it in GDB. Let's go GDB. We'll hit continue. And now that we're here, we can, for example, this bin sh address. Well, what we could do actually, we could have found this in here. So let's do search -s, and then we'll put in /bin/sh, and the offset that we have here, does that match up? It looks like it does to me. So you can see we've got the same offset there. Another thing we could have done, we could have said x over s and that address, and we'll see that, yeah, that's where bin sh is. We could have a look then, look at our system address here and say disassemble, and we can see that that is our libc system, and we can go through and we can verify the same for our each of our addresses. Cool, that's all working as we would like it to. So our final stage here is to do our second payload. Now that we've got all of our addresses, we can call this system function and pass in the bin sh string to get our shell. And we're going to do this just as we did up here, so we're going to build a new payload. And let's get rid of all this stuff in here, but the same idea, we're going to be sending it at this offset. We're going to be needing to put in these parameters again, so let's grab these as well. Just copy and paste those. And what do we want to put in our payload this time? Well, we know that we want to call our system function, so we can put in our system address. But in order to call our system function, we also want to put our bin sh address into the correct register. It needs to go in the RDI register. So we need to pop it into the RDI, and we grabbed a pop RDI gadget here. So we can pop RDI, and the next value that we place here is going to get popped into the RDI. So let's put our bin sh, and then system's going to get called, and it's going to look in the RDI and see, alright, I'm calling system with this string, and that string is going to hopefully return us a shell. Should we test this out? So we'll try to run this, python star.py, and you'll see this actually freezes here. So if we go back to our code, whenever we do io.receive here, we're actually receiving this arrow, as this angular bracket as well. So in waiting for this, this is never going to arrive, so we're just going to send a line without sending that at all. Let's do that. Go back and run that. And here we have switched into interactive mode. Looks like we have a shell. Let's try and list. Yep, we can list ID, and yeah, we have a shell. Cool, so that's all working. Let's see if we can test it remotely. So we'll go back here, we'll spawn an instance, and we'll copy the address, and we should just be able to plug everything in as it is here. If we do python star remote capital letters, paste in our server and address separated by a space, and if we run that, we get to our interactive here, but we get an error. It's a segmentation fault, and we don't actually get any. We don't have a shell. If we try to do ID, ls, and things like that, we're not getting anything back. So one of the issues here is that you need to identify what version of libc is running, and we can do that using this URL here, libc.blukat.me, and we can let me clear this and show how we can do this. So if we go back, oh, I should have kept that open. Let me run that again. We're going to go back and we're going to grab our leaked got address here. So we grab our leaked got address, and we want to, in our query, we want to paste in the address here, and we want to say write. And if we hit find, this will bring a list of all the possible libc libraries that this could be, and we basically go through these different libraries and try the offsets. So if we click on one of them, we'll see here that the system offset is 4F550. Let's click on this one. You can see it's a different offset, and as we go through, we have different offsets to test out. So I've already been through this and identified that it's this one at the bottom. So if we go and grab some of these values and plug them in, so let's grab this offset here. This is the right offset, and if we go back, and whenever we're subtracting here, this is what we're going to subtract instead, because this is the version of libc that they're using. There's our bin sh string, so we can grab that as well, and this is the correct offset to bin sh. And what else? The system as well. So let's grab system, we'll copy that, and we can paste this in here. And now if we try to run this again, you'll see we didn't get any errors. If we list, we've actually found that we are able to get into our flag. We can do cat flag.txt, and there's our flag for us. So that's how we can solve that. What I'm going to do now, actually, boom, I just added some comments to this script, and I'll be putting this script online as, I'll just call it shootingstar.py, and I'm also going to add another script. I'm about to do a little bonus section where we're going to try and automate this a bit more. We've got to manually put in addresses and stuff here, but actually we can use the ROP objects, as we have done in some other examples and in some other Pwn challenges, to automate a lot of this process and call in system and things like that. And we can also, if we go back to the libc here, we can download this library. So a possibility for us is that we could get things working locally by loading in our libc library, and once it's working locally, we could just find out what the leaked write address is and identify what possible libraries it could be. We could download all of these libraries, and then we could just run our script against each library until one of them works, rather than going through and manually updating all these offsets. I don't know if that makes sense. It'll make more sense as we go through it here. Let's put together a new script. Okay, so I've already put together a script here. I've called it ropstar. And let me just go through and explain, rather than typing all this out. I'll just go through and explain it. And actually, let's open up our Codium shooting star. Star.py. Let's open that as well, just so we can go through and actually compare them side by side. Can I get a good... Oh, I don't know how to split these screens. There we go. Okay, so we've got a ropstar. This is our new one on the left, and we've got our old one on the right. Let's go and see what's different. And if we get to the same locations, the first thing you'll notice here is that we've loaded libc library as an elf, and I've loaded it in with the address. If we go back and do ldd shooting star, this is just the location of our libc library. So that's our local library, but what we can also do here, let's go and... In fact, let's get it working first locally. That's fine. Let me not talk about too many things at once. Basically, we'll be able to swap this between local and remote quite easily, which is what we were kind of just talking about. We also create a ROP object this time, which we didn't do here. And in creating a ROP object, it means we can search through for gadgets. So if I do rop.gadgets and print those out, I'll be able to get a list of all the gadgets that are available to us. It doesn't actually contain all the gadgets that are in ropper, so sometimes if your gadget's like a bit more rare or longer gadget, you might need to still find the address of it manually. But essentially here, rather than putting in the address of our pop RSI R15 manually, we're searching for it with the rop.findGadget function. And then, instead of doing this payload here, we actually do the payload very similarly. So we're passing in the same parameters, but we're just doing rop.raw, and then we pass that through, just creating a chain. So that's just going to it's just going to convert that into the raw bytes. So everything that's happening here is the same as happening here. I've put a little note here. It would be cool if we could change this to rop.call, which would then be able to pass in this as a function and this as a parameter, but I couldn't get it working. If anybody can get it working or knows any cool tricks they want to fill me in on, I'm always happy to take feedback and suggestions. But anyway, let's keep moving down and see where the main magic happens here. So you can see in our previous example, what we did is we got the leaked address, just like we're doing here. We're doing all this the same, so we get the leaked address. But in our last example then, we went and manually calculated the libc base and the system address and the bin.sh address. What we can do now, because we've loaded our libc library here as an elf, we've loaded it, we have all the functions and things like that, but we don't know where the actual base address is. But once we've leaked it, right here, we've got the leaked address, we can just say, well, let's set the address of this, let's set the base address of this elf file, the libc, to equal this leaked address. So we subtract the write address from the got.write address, just as we've done right here, and that gets us the base. But once we've got the base, we're actually assigning it to this elf file, to our libc elf. And that means that whenever we want to call system and things like that, we don't even need to find the address. You can see right down here what I've done is I've just created a new ROP object from the libc, and we're calling rop.system, and it's going to do everything it needs to for us in terms of we don't need to find a gadget to pop bin.sh into the RDI. And in fact, the bin.sh, we don't even need to find the address of it, because we can use the search function here to find that in libc. And then we just send this through as a payload. So I think you can see from the difference there, that's quite a lot of work taken off of our taken away from what we needed to do. Let's try and run this locally and see how it goes. We'll do Python ropstar, and we have our shell. If we go up and try and have a look at it here, let's see, did it actually dump out the ROP objects that it created? There was a pop RSI. Oh, it didn't seem to. Okay, let's go back to our code, and we can say, let's say here for the ROP system bit, let's say rop.dump. Do we need to print? Might be better pretty printing it, I'm not too sure. Let's try that. And you can see here the ROP chain that it created, whenever we called rop.system and passed in this search for bin.sh, what it's actually done behind the scenes is it's gone and compiled a ROP chain which says pop RDI, and what it's going to pop into the RDI is going to be the address of the bin.sh, which we've told it to search for, and then call system. And it's just doing all that for us, which is cool. But now if we try and do this and say remote, let's grab the, remote, let's grab this address again, paste that in, and you get the segmentation fault, right? Because the libc version they're using is not the same version that we're using. So let's try and fix that. So we can go back to our libc database here, we've got the download link, so I'm going to copy that link and we'll do wget, download that now. And in our code, we're just going to go back to our code. Let me close down this original, the star one, and take this print rop.dump out of there. And what we want to do here is basically just change this from local to remote. Where did I put this flag? So we were loading our libc library from our system, but we've just downloaded this local library, as you can see here. So let's comment out our system libc address or file location, and let's put in this local location now. And if we do that and run it, you'll see now we've got no error. We can list and we can cat the flag.txt if we type it correctly. And there we go. So yeah, I'll put both of these scripts up. If anybody has any, particularly in PwnTools, if there's anything, any cool tricks that I'm missing, I'm always looking to hear. If you solve this challenge in a different way to me as well, I'd like to hear about that. And I hope you've enjoyed the video. Any questions, comments, leave them down below. Thanks.